All right, everybody. So let's start the seminar. We have as our guest Dr. Jia Zhao. He received his PhD in computational applied mathematics from University of South Carolina at Columbia in 2015. Then he was a postdoc at the University of North Carolina at Chapel Hill for 2 years. And then after that, he joined Utah State University as an assistant professor. So his research is an expert in phase field modeling, numerical methods, computational modeling of complex multi-phase fluids with application also in life sciences. So his work has been funded by multiple sources. And I'd like to say that we have been following his work. It's of very high quality in phase field modeling. So we are very happy that he accepted our invitation to give the talk here in our SciML seminar series. So thanks, Jia, and the floor is yours.
Yeah, thanks for the invitation and introduction. Thanks everyone for being here. Today I'm going to talk about some of our work on, we try to either solve or learn phase field models with this newly developed physics-informed neural network. So as introduced, my background is more like in computational modeling on complex fluid. We try to develop phase field models and try to develop numerical algorithm, do simulation applications. But with this popularity of this PIN, right, physics-informed neural network, and then we realized, can we do something with that, and combined with my research interest. That's kind of the motivation. We kind of started, I think, 2 years ago with my former master student, Kobe White. He got his master last year, and then he went to PNNL as a data scientist right now. So currently, my another master student, Gerard Mao, is working on this. The reason I use master student on this project, it turns out the master student is more good at programming than the PhDs. Turns out they are doing great so far. Let's get into it. I think you guys are definitely expert, more expert in than me in terms of this machine learning, data science, and neural networks. But I think I can share some insight in terms of phase field models, right? So how maybe you can apply your tools into solving phase field model. Well, because the phase field model is a huge field, there are lots of equations besides the Kahn-Hiller and Allen-Kahn equations. There are lots of equations and lots of problems unsolved. Well, let's get into it. I briefly introduced the phase field model. Then I try to introduce the idea how we can use apply neural network on the phase field models. So for the phase field model, mainly there are several steps. You try to develop a phase field model. So first of all, you need to introduce a phase variable. Here we call the phi. So it's a function of both space and time. And then we introduce artificial parameter, epsilon. So epsilon is a fixed, but it's artificial. So if you look at the figure below here, right? So in reality, if you have two immersible fluid or immersible material, material 1 and material 2. So the phi try to represent the volume fraction of material 1. So we know phi goes from 1, right? And the interface, all of a sudden it drops to 0, right? Because at next, there will be the volume fraction of material 1 will be 0. So in this case, if you use this phase variable to represent the volume fraction of one material, and turns out there is some a singularity, right? At least it's not smooth, not differentiable, and then there's also problem. Well, the whole idea of phase field, or sometimes people call it diffuse interface model, is that they try to introduce a diffuse interface, with a limited thickness epsilon, and then your phi will goes from 1 to 0 very smoothly, in this interface thickness epsilon. Well, we have to make sure this epsilon is much more smaller, right, than the scale, the whole domain you're talking about. Otherwise, the problem, this will not convert to the original problem. So once we have the phase variable and the artificial parameter try to mimic the interface thickness, we need to propose an evolution equation for the phase variable. So basically, once you have the variable, you need a differential equation, a partial differential equation for phi, and then so the interface can be retrieved by the level set phi equals to 1/2. Right? So here phi equals 1, that's one phase. Phi equals 0, that's another phase. So when phi equals 1/2, that's the interface in between. So this is tracked implicitly. So we didn't really track the interface. Like we didn't really follow the interface explicitly. So instead, we try to reach the like try to solve a differential equation, and then we try to retrieve the interface by this level set. So that's the whole idea of phase field model. And then the main difficulty is how we can propose a phase field model. Well, the reason I introduce this is because this is the essential later we will try to solve this using neural network, because you will see like in most scenario, this is kind of like you have multi-scale, right? Like in certain domain is constant, right? But only in this small like interface, this will be non-constant, right? So that's in terms like spatially, this is like a multi-scale problem. Okay, then how we can propose the phase field equation? So in general, the phase field equation can be written in this generic form. Okay, so we have the phase variable, and then we need like two more items. One is the so-called free energy. Okay, the other is the so-called mobility operator. So once you have this, you plug into this generic equation. Sometimes people call this gradient flow. Okay, but of course, phase field model can be more way much more than gradient flows, because we can add more component into it. Okay, so basically, once you have free energy, have mobility, you plug in. By the way, this partial f partial psi, that's the like a functional derivative. So once you have this equation, you end up with, let's say, for example, let me move this away. For example, if you have a free energy like this so-called Ginzburg-Landau free energy, and you have a mobility operator, lambda Laplacian operator, you plug in, you get the so-called Cahn-Giller equation, right? So or you can use something else like this one, right? This one is used to study the molecular beam epitaxy growth. You have the free energy, your mobility is just like negative or constant. You plug in, you get the MB model. So in this case, basically you specify your free energy and the mobility operator, you end up with a different model. That's the reason I mentioned like this is a huge field in phase field models, because there are a variety of free energies and a variety of mobilities, right? You plug in, you get a model, right? The question is how we can solve those, right? Or how we can develop models, like figure out more physical meaningful free energy and the operators. Okay. So one thing I mentioned is like this constraint, right? I think this will be very helpful for your group is, for the phase field model, people always talk about the energy dissipation. So in this case, if we assume the temperature is constant, okay, we only can assume this non-isothermal case, okay, sorry, isothermal case. And then like we talk about the free energy is non-increasing in time, right? Because you talk about the time rate of change of the free energy with respect to time. The domain is fixed. So you plug the change rule into it, right? So you have partial f, partial phi, partial phi, partial t. Partial phi, partial t can be replaced by the right hand side, right? So we have this more like an inner product. So because if you make an assumption about the mobility operator is a semi-negative definite, and then the whole thing is less than 0. So this is like a golden principle in the phase field models. Like, either you want to develop a phase field model, or like you want to solve a phase field model, you probably want to make sure, they are so-called thermodynamically consistent, right? They follow this second law of thermodynamics. Okay, so of course, like, right now, it's still generic, right? So like how we can propose the mobility, right? How we can propose the free energy. Well, there are lots of, arguments or literature, but, our time is limited. Let me just briefly introduce this so-called free energy. So most of the time, the free energy are like proposed like more like phenomenologically, right? Because you have a certain system, we can, do some like a generic analogy, right? They end up with some free energy. But for certain free energy, they can propose by physical argument. Like, if we talk about the total volume of phase one, so because the phi is the volume fraction, right, for phase one. So if you take integration on the whole space, that's the total volume of phase one. Or you can talk about the surface energy, the surface tension energy for the interface. So gamma is the surface tension, and you take an integration on the whole surface of your interface. But this is because the whole surface, as I said, we didn't really track the interface. So what we can do is like we introduce a delta function, try to identify the interface. So we move from this surface integral to a bulk integral. And this delta function can be approximated by certain term with certain argument. Or the argument is when epsilon goes to 0, and this converts to a delta function. So that's the case, we have this Ginsburg-Landau free energy to mimic, the surface tension free energy of the two immersible fluids. Okay, of course we can talk about the bending energy, like we have the bending rigidity and the mean curvature square. So the mean curvature, is defined by negative divergence of the unit normal, right? The unit normal can be approximated by this negative gradient phi over gradient phi absolute values, right? So if you plug in, you do some, approximations, you can end up with this, free energy. But in this sense, even though like for certain case, right, the free energy are like are phenomenological, but for certain case, they have their physical augment, they have their meanings there. Okay, that's pretty much I want to introduce on the phase field models. This gives you the whole idea. If you have the free energy, you have the mobility operator, you plug in, you get a phase field model. Okay, and then let's talk about how we can use the neural network, right, to work out the phase field models. When I was let's say I'm first introduced to the neural network, people usually say, okay, you have an input and you have black box and you get the output, right? Like, you have an image of a cat, you go through this black box and this black box will tell you whether, it's a cat or not. And if this doesn't work, you kind of tune the parameter a little bit and then until it works, right? So that's pretty much like all my students, when I meet my students, they want to work with me, I ask them, what's your idea of neural network, right? That's what they're saying. It's a black box, you need to tune it until it works. And pretty much if you go to many talks, they give it this way. But as a mathematician, I think, like a more like a mathematical understanding of neural network is pretty much it's a function, right? So you give me an input, right? You give me an input with a certain dimension, and I give you an output, right? So it's only a mapping, right? It's a function. And for this function, there are some free parameter, right, which can be tuned. So usually, like for mathematician, we learn like approximation theories. Like, you want to approximate a function, you figure out a basis, right? You do a linear combination with the basis, right? Like you figure out the coefficient, and then you can fit the certain function. But the difficulty for the neural network is it's not a composition. It's not a linear combination of basis. It's a composition of function. So pretty much you have a function, and if this function is not powerful enough, you use this function the output and another function the input, right? You do the composition, right? And then like you keep doing this composition until it works. Of course, like there are some theory called the universal approximation theory says, okay, so for this neural network, it can basically approximate, right, an arbitrary function to arbitrary accuracy you like. So that's what why people like saying like a neural network is powerful, because they kind of like justified by universal approximation theory. So if we agree with this, of course, why don't we use this neural network, right, to approximate the solution of a certain equation? Like this one, this is the simple one. This is the only OD initial value problem. Like we know this neural network is powerful enough to approximate the solution, right? So of course, like if we know what the solution is, which is cheating, right? Like because we don't really know the solution of this differential equation. So if we know the solution, we can fit this neural network with this solution, right? Do this so-called pretty much like least square minimization, and of course it will converge, right? Because this is more or less like it's a quadratic, right? So we can make it convert. We figure out this theta. But the problem is like we don't really know. We don't really know this solution, right? Otherwise, we don't really bother to solve this equation. So if we don't know the solution for the equation, but we also want to figure out this theta, right? Because I'm saying we want to figure out the theta such that this neural network can approximate this like function. Okay, what can we do? Well, the only information we know. So if this neural network is the solution to the initial value problem, it should satisfy the initial value and the whole equation, right? So that's the reason, if I plug in this network into this equation and into the initial value, we try to minimize, right, this norm. And if we can minimize it, we can figure out this theta, right? We know this theta exists, right? that's the like the hope, not the hope. That's the reason we want to do this. We know theta exists because if we do this, if we minimize this, it can converge, right? So we know it exists, but the problem is how we can find out theta, right? How we can really find it out. Well, this is the continuous problem. It's really basically not practical to solve. Numerically, what we can do? What we can do is like try to approximate this L2 norm, right? And approximate this like this a square. Well, the way we can do is we sample, right? We sample some data from this time, like from 0 to t, and we sample some data to approximate this integral. We sample some data to approximate this square. And I will try to minimize this. And this is pretty much durable then. And we try to minimize this and try to, once it's converged, we figure out the theta and we figure out a solution for it. And this idea is really not new. If you at least I can figure out a final paper back to 1998. Okay, they use this idea to solve ODEs. Okay, so if this works, can we like push the boundary, right? Like since it works, can we solve this more complicated problem? In my case, is a phase field, which I realized that this is a really bad choice because it takes us for like this. Like when we read this PIN paper, right? Like it seems really promising. You can solve most of the equations they showed. And then I told my student, go ahead and try to solve an Allen-Kankira equation, right? And then we can move on to solve more complicated case. But it turns out it's a different story. Well, let's see what was the reason. I think we do have some feelings why it doesn't work that well. Okay, so this is the generic phase field model I talked about. Okay, so we have this more like a gradient flow. We have free energy. We have mobility. We have initial value, right? We have boundary condition. So this boundary condition could be Neumann, could be Dirichlet, could be like a mixed Robin boundary conditions. Okay, so if we think about the classical numerical method, right? The classical so-called least square method, right? It's there, right? Like you try to figure out a solution in certain like domain, in certain space, such that this norm is minimized, right? So like this phi satisfies the equation, it satisfies the initial condition, and satisfies the boundary conditions. That's the so-called classical least square method. And you plug in, so basically what people do is like people assume this phi, right, is a linear combination of certain bases, right? And then all of a sudden, this problem, convert into like you minimize a least square problem, right? Because you only have like a handful of unknown coefficient, right? Because if you assume phi is a linear combination of certain bases, where this coefficient is a function of time, you plug in, you can actually more like reduce the problem order into a lower dimension. But the internal neural network, okay, we try to use this n to approximate this phi, right? So instead of looking for a phi, we're looking for theta. Okay, theta is the free parameter in my case. Beta is the hyperparameter. Once you fix it, it's fixed. But theta is something you can train. Okay, and then you try to minimize this new like loss function where you replace all these phis with neural network. Okay, so again, the question is, we know the theta exists, right? Because like if you know the solution, and you try to fit your n to the solution, it's a piece of cake. It's trivial, right? You definitely can make it convert, figure out your theta. But the question is, you don't know the solution. You don't know the solution, and you only know this n, right? Should satisfy the equation, should satisfy the initial condition, should satisfy the boundary condition, right? That's what we know. So that's the reason we try to minimize this. Okay, and then like of course, like numerically, right? You want to like because you cannot solve this continuously, right? These are all norms. What you can do is like, you do sampling, right? In this space, you sample, right? In this space, you sample. In this space, you sample, and then you try to approximate all these norms, right? With your sample data. So that's the I think it didn't show my sorry, it didn't show the I referred to this PIN paper, PIN paper. So if you propose a neural network, right, to approximate the solution, and then you sample data from the initial condition, you sample data from the boundary, you sample data from the collocation point inside the domain, and you try to approximate this norm, right? Just wrote it down numerically, right? And then this is the so-called mean least square, right? Like loss function. You try to minimize it, and that's the whole idea in this PIN paper, which is really popular, right? I think you guys definitely know this. It's why like there are lots of people following this work and try to move on. But the question is, once my student, plug in, right, try to like, replicate and then, to solve this problem, and it doesn't really work, right? Here is this blue curve is the exact solution. This red curve is the neural network solutions. So it doesn't really work, right? So what's the problem, right? And then, definitely we'll try to figure out some ways, right, to make it work. Like, there are lots of ideas there, like adding weights in the loss. You do mini batching on the data sampling, right? Or you do like adaptive samplings, or you can do like use different like a gradient descent, stochastic gradient descent method, try to make it work, right? Of course, sometimes it works, right? Like, if you really fine tune your hyperparameter, right? Fine tune your training strategy, it might work. But still keep in mind, there exists, right? So it turns out that this is really like a nothing fancy, right? Like, there is a theta over there, or maybe there are multiple thetas, right? Like over there. And of course, like this neural network can approximate the solution. But the question is how we can figure out this theta. And we have the hope, right? We have the hope like stochastic gradient descent will send us there. But that's based on, if you know the information about the solution, right? But if you don't know information about solution, you can only like with a certain this kind of constraints, and you try to make it converge. Or will this work? Well, it turns out sometimes it works, right? Sometimes it doesn't. But what's the whole reason, right? Why it won't work in the phase field models? We didn't really realize this until like later. Pretty much like my students spend like a year and a half, try all kinds of approach, and it doesn't really work. And we propose something new. I would say our solution is not a real solution, right? It's more like we have some compromise, and like we forget about the efficiency, right? We forget about like all this like a generality. First of all, we want to make it work, right? So that it works, then we can move on to make it better. And the reason, let me try to explain the reason we kind of like realized, or let's see whether it's true or not, right? I think you guys also like work on this phase field model for a while. Well, the reason I think is because the solution for the phase field, okay, it's multi-scale, so both spatially and temporally. Okay, so this is a huge problem, because if we look at the original problem, right, where PNN can work well, right? It's pretty much, if you have you don't have this like much like oscillation in your solution. In particular, okay, let's talk about both. Okay, for the spatial scale, that's very straightforward, right? Because most of the time you have 0, most of the time you have 1, but there's only certain case it's like between 0 and 1, and it's a thin layer, and it's also changing rapidly, right? It's not like a fixed there. It's like moving with time and changing with this interface. So that's the spatial level. So time level, okay, the time level is more important, because if people working on phase field, they will know, okay, so there most of the time there are power laws for the phase field dynamic. By power law, I mean the phase field model usually like evolve very rapidly at the beginning, right? And eventually they have like a lower times, like a smaller time scale. Like, let's say for this coarsening, right, or computer dynamic, okay, the x-axis is the log time, okay, the y-axis, this is the log energy, this is the log roughness. The log roughness basically tells you the spatial scale, okay, like the spatial scale of your solution. So the energy is like in terms of power, you see like sorry, it's very tiny. I think it's either -1/2 or -1/3. Okay, so it's like evolving with a certain power, which means like at the beginning it's evolving rapidly, right, and later it's evolving slower and slower. Okay, that's the so-called like time scale. For the spatial scale, you see, right, with at the beginning, right, it's very pretty much like randomly, because you have interface everywhere, right, and the interface will shrink, and like later you have like a more coarse, like more smooth the domain. So it's also like a changing like with certain power. So we cannot really treat this like time and space equally, right? That's my whole point. So if you like just like a randomly sample, because randomly sampling is treating them equally, and like you basically wasting most of the sampling effort, right, to some place where it's either 0 or 1, which doesn't help, right? You really want to put your sample at the interface. Well, the problem is you don't really know where the interface is, right? So the interface is also evolving with time. Okay, and that's not even enough. Okay, the other like really like important case is the phase field dynamic strongly depends on the initial and the boundary condition. Well, if you ever simulate a phase field model, if you have a initial condition, right, you run it for a while, okay, but if you perturb the initial condition a little bit, okay, you rewrite for like a certain time, your solution might be totally different. Okay, also for certain cases they are similar. Let's say if the the spatial pattern is simple, right? So basically, if your initial condition perturbed, okay, your dynamic will change slowly. But if you have lots of interface, right, it's more complicated scenario. Your initial condition perturb a little bit, you might have a totally different like dynamic later. Okay, and that's extremely important because you imagine, right? So if you put your constraint like on here, right? This is the least square. What do we mean by least square? Which means like we don't really care it's accurate, right? Like if at initial condition you have a certain approximation, we allow some error, right? And with time passing by, we'll allow some error, right? So that the total error, is under control. But however, if you, let's say, if at the time t0, right, your approximation is wrong, is like is off, and you based on that, you try to use the equation, right, to evolve for like t1, t2, and that's totally wrong because that's not exactly what we want at all, right? And that's the main reason, the main reason why phase field model is really hard to solve using neural network. And for certain hyperbolic equation, like you have wave traveling, right? That's relatively easy because if you fix your initial condition, your certain wave pattern, right? And this wave is evolved, the shape doesn't really change, right? So your interface is basically falling, you can figure out the traveling wave, right? You know certain like line, that's where your wave is like traveling with time and space. But for phase field model, it's different. Right? You cannot really predict what's going to happen next, right, with the interface. So that's what we were like, okay, you cannot like just like throw a bunch of points and try to brute force figure out this data, and that at least doesn't make sense to us. And then like my students say, okay, why don't we just treat like cheat a little bit, was not really like solving like because this problem is too difficult, right? Because there's like a really time scale there. Why don't we put more effort at the beginning, right? Like we have more points at the beginning because it's evolving more rapidly, and then we put less point later, right? And in that case, we might be able to capture the dynamic, or more like also like for the space, right? Like at the beginning you do like a random sampling, but that's definitely not enough because the initial sampling, right, it's more like a uniform sample, right? You don't really like care where the interface is. However, the interface matters, right? So in that case, you do need a resample, right? Like figure out where the interface is, either by your energy, or by your spatial derivatives. Of course, like this weight is also important. You need like add much more weight at the initial value and boundary condition, because if this is off, your solution will be off, right? So this is a very like important, and that's pretty much like we realize this. Let's cheat a little bit. For spatial sampling, I think this is very standard, right? But one thing is like we try to do the sampling based on the spatial resolution. Like if the derivative is high, or like we can use either the energy, right? Like local energy at that place if it's changing rapidly, and then we need more like sample data for sure. But do remember, okay, we don't really know, right? We don't really know the solution. So even at this resampling, we're using our approximation to approximate, right? We're like using like our approximation to the solution. The neural network tries to say, okay, if there is a high derivative, but this neural network might be actually wrong, right? Because you don't really know the solution. So which means that this resampling might not be correct, right? If you really look at the whole solution, maybe there's not interface, maybe somewhere way off, right? So if you only do spatial sampling, it still doesn't work because your network might not be true. So here we came up, why don't we put more emphasis on the beginning and put less emphasis at the end? That's I think that's the key point of this work, is we put more emphasis at the beginning. Like we have two approach, but both approach, I would say, they're not efficient, right? Because it definitely like takes more effort. But I would say at least it works, right? At least it works. At least you can solve the problem. And then based on that, definitely we can, maybe put more effort, like try to make it much better, much like efficient. Okay. The first idea is like we first of all, we only sample data at the beginning, and then we try to make sure, okay, our network can approximate the solution at the beginning well, and then we make the domain larger and larger, and until it converts. Okay. And the second approach, I think, is more interesting. Is we only solve this problem in a small domain. I think even though it's a hand waving approach, but I think it's more like a smart approach, right? Because the whole goal is you want to solve this equation, right? But nobody tells you have to solve this simultaneously, right? That doesn't really make sense. So if we can like classical numerical method, right? And like a classical numerical approach to solve differential equation, we do have least square method, but nobody uses it, right? The reason is it's not efficient. People use the finite difference, finite element, or spectral. They try to like discretize the space and the time domain. And there's a reason, right? Because it's more like efficient in the end, right? So here we basically we try to truncate the domain into several pieces. Of course, like this is a more like a lazy approach. As I mentioned, because the time scale, like you have really fine time scale at the beginning, right? You have coarse time scale at the end, which means that you probably want to have really fine steps at the beginning, right? And then later you make your step size larger and larger. Let's say maybe you do 0, like a point 001, and then maybe point 002, and then later you can use bigger time steps. You have multiple networks, and then like with the first network, once we train this very well, we use this output of the first network as the input of the second. And this is also extremely important. Well, the reason I mentioned is the phase field model dynamic really depends on the initial condition, right? Which means if I use a small domain, I train it, okay, my output will be a good approximation to the solution at this point. So this can be used as the initial condition for the next network to continue the training, okay, right? Because because if I'm training a small domain, I'm pretty confident, okay, the output of the first neural network, right, will be a good approximation for the solution at point 1. And then I use this as the initial condition for next network, right? And then next network can be trained well. But the classical approach, if you use the whole domain, okay, when you like a sampling data here, right? You sampling data here, you use the equation to minimize the error. You're using you're actually using the neural network to approximate the solution here, which might not be true, right? Because the domain is huge, this approximation might not be true, and then later it's totally off. That's the reason most of the time it won't convert, because you're using the wrong initial condition, for the later dynamics. Okay, so with this in mind, we pretty much I'm not saying we can solve every like a phase field model, right? At least with some fine tuning, we can solve this like 1D Allen-Kahn with a different initial condition. We can solve 3D like this classical benchmark problem. If you have a sphere, right, will shrink. The radius is decreasing following certain laws. Okay, this is the errors. Okay, the pointwise errors. The first one is about 10 to the negative 3, right? So we can also solve Allen-Kahn. You're shrinking in an L shape. Well, I would say the advantage of this idea is like we have one code but can solve all kinds of phase field problems, right? That's pretty much the advantage, even though it might not be as efficient, right, as a classical numerical method. But at least you have one code can solve 1D, 2D, 3D, or like a different geometry. You basically just need to sample, right? So that you can do a sampling well, and you do this adaptive, you should be fine. Okay, and then we can do concatenator. But concatenator is a different story, right? Because for concatenator there are more tricks. So first of all, the concatenator you have high order derivative, right? So you don't really want take more derivatives on your neural network, because that will be very expensive to calculate. So what the idea here is we introduce multiple network. Okay, you can introduce a mu network to represent the the partial f partial g, right? You introduce another phi, and then you try to do this least square. Well, it's not as good as Allen-Kahn, but at least it give you the like let's say qualitative dynamics. You can see this two kissing bubble into a single ones, and this Allen-Kahn dynamics. You can also solve for some other case, but I said it's not like a general enough to solve everything. So you do need like fine tuning on this like time steps and the sampling and the weights, this kind of stuff. There's no general ideas so far, but at least we can solve some of these problems. Yeah, that's pretty much my first part. I think I take too much time. Don't have enough time for my second part. The second part is we try to like discover the phase field model, based on the image data. Well, this is actually I would say this is the whole motivation of me like getting into the neural network, because we have got a NSF founded ground, so we try to like develop phase field models, try to study this so-called liquid-liquid phase separations, because recently the biologists they realized, okay, so inside the cell there are lots of organelles. They're actually membraneless. Even like when I was taking the biology, right, like in high school and college, over the textbook, people always say there are lots of like membrane organelles, right, like the cell used to do the function. But recently they realized, okay, there are lots of membraneless organelles, like the RNA and the protein, they will like bind and unbind. They form this dynamically droplet and form lots of like chemical reaction on the inside. So once they finish their reaction, they they dismiss into the cell. So this some figure, if you increase the width rate is the protein, okay, the clearance rate is the RNA. If you increase, you see this phase separation, and you have this droplet. And because of the this is conserved, right, and you have phase separation. Then this pretty much we want to like develop a phase field model, try to like understand the mechanism underneath. So that's the whole goal. But that's like very ambitious. So far we do have some results, but not good enough yet. But at least we have some application using the neural network. Or the problem setup is okay. So imagine I have this my collaborator, right? They can take some snapshot, right, of this this phase separations. Like you take some snapshot image, right, at different time, right? So this image can come from like the same time sequence or come from different time sequence. Can we actually recover a phase field model from it, right? So here my setup is I have a collection of data pairs. So this is my first image, my second image, and the time lag between these two images taken. Okay, I can have multiple pairs. Okay, and I assume okay this dynamic, right, follow a phase field model. Of course, like this is a strong assumption. And then can I recover this free energy and mobility? Okay, so that's the whole idea. Of course, like we have to like reformulate this, right, more rigorous in mathematics so we can solve it. So here is my like more like a toy model. I can solve. So basically, okay, let's say if I have this equation, okay, where this is basically if you have the free energy, right, you take the derivative, you end up with two parts. One is this G, which is known, because even we want to discover a model, right? We don't want to start with a scratch. We want to like based on the known knowledge first, right? Because we know something already. You should satisfy certain like laws, and that's the known part. But this is the unknown. Okay, this F is unknown, and the way is like if you give me certain image data pairs, can I recover this F? Okay, can I recover this in the physics we call bulk potential? Okay, can I recover this bulk potential? Well, the idea is actually it's followed from the numerical inspiration. Like if I have this phase field model, right, how I can solve it, right? Like if I have this model, how I can really like solve this numerically? Because in the end, right, we need a loss function. We need this loss function based on the equation. So it's pretty much like you have to go back to the first part, the numerical part. So the next few slides is basically inspired by this numerical method. So I don't know you guys background, but let's just briefly introduce this because this is very important. So you have this known part, you have this unknown part, right? This known part can be split into two parts. One is a linear operator, the other is non-linear. Okay, and then we do this backward Euler. Okay, just basic finite difference matter. We have this numerical scheme, and then you rearrange this a little bit. Okay, so if you know the solution at Ti, you can numerically solve your solution at Ti plus delta I with this numerical scheme. Okay, because here I made an assumption this operator is invertible, so that's the reason I can write down this way. Okay, so that's inspired by that's basically the first order numerical scheme to solve phase field model. Okay, now let's come back to our let's come back to how we can identify the bulk potential. Okay, based on the image data I have. Okay, here's the whole story. Okay. So let's say numerically, okay, if I have phi I, right, my solution at Ti, and I know the time step, I want to like time march, okay. So numerically, I can approximate the solution at a T, like a T2 with this numerical scheme, right? That's the scheme I just wrote down. Of course, I don't know this bulk potential yet. So this potential is a neural network, okay. But this is this is like a feed forward, right? If I plug in, I can get this directly. Okay, that's my prediction. Okay, using a neural network, and this is my known data. right? Because I said I have a data pair. I know the image at T1, I know the image at T2, right? So this line is my prediction using neural network, and this is the data I know. And that's the reason I can minimize this mean square error, right? By minimize this mean square error, pretty much you minimize looking for the theta, right? Because the only unknown, the only like freedom is theta in the neural network. So that's the reason if I minimize this least square, once it's converged, right, I can get my theta and plug in, I get my neural network for my bulk potential, and then I recover this the whole model. Okay, that's the whole idea here, and it turns out this is very efficient. Well, let me explain why this is efficient, because like this is also related with the phase field models. For the phase field model, there's a huge community that try to develop numerical schemes, and it's known. Okay, if you want to solve this phase field model, use the explicit numerical scheme, like forward Euler. And there's a huge constraint on the time step. Again, this related with what I'm saying. If your initial condition, right, you have some error, if you merge a time step, then it will change dramatically. So you really want to make it accurate, right? So that's the reason, if you want to solve phase field model, usually people use the implicit numerical scheme. So it's more stable, right? So you can use the large time step. So this idea I give here, this is the implicit, because I did the inverse for the operator. Okay, this is the implicit, which means like this is a very good approximation for phi2, even with large time steps. Okay, and that's the reason I can solve minimize this and get my neural network, and it's very accurate. Of course, like what if like for the data sampling, right? You have really huge time lag, like because my collaborators always complain, right? They don't have that enough resource, to take a snapshot like every second, right? They have to like to do time shot like maybe every minute, or maybe even hours, or maybe even days, right? Because the resource is very limited. So what if your image have a really long time lag, right? You have a certain image, but can we do that? Well, it seems we all can also do. We just introduce the so-called recursive idea. Well, because if you have a really huge time step, you just truncate this time step into multiple small steps, right? And then you time merge your numerical scheme one by one. Let's say you have k time steps, right? Like the delta I, you divide the delta I into k steps, and then you try to use this solver to predict the solution for like a small slice, and then a small slice until you repeat the case. We call it recursive. Okay, so this is our prediction for phi2, and that's the known data for phi2. The only unknown is the freedom in the neural network, the free parameter, and then we minimize this. Okay. Of course, like we can introduce more, right? Like longer CUDA, because there are lots of numerical method in the textbook. So, but let's see what it works, how it works. So this is the first example. So I have Allen Kahn equation, right? I solved this Allen Kahn equation. By the way, our method only works for the synthetic data. For the real data, we're still working on it. Okay, so this is the synthetic data we generated. We solve Allen Kahn equation, right? We have a bunch of image, and then we hide the Allen Kahn equation, assuming we don't know what the equation is, right? Can we recover this bulk potential, this double wire potential or not, right? But only based on the image snapshot. Okay, here are some numerical tests. Okay, so if I use a longer CUDA, method, okay, the longer CUDA method, and if the image with the time step snapshot with delta, with 0.05, okay, it works. Okay, well, I can predict this double while all this bulk potential very well. But if the time step is larger and larger, let's say we have like a time step delta 5. Basically, I'm sampling, right, more sparsely. Like I take a snap image, right. After a long time, I take another image, and then after a long time, I take another image, and this longer CUDA won't work. Won't figure out this bulk potential, and it's reasonable because I said we really the explicit numerical method, right? They have a strong constraint on the time step. For the longer CUDA method, if it's implicit, right? So yeah, you really need a really fine time step to make sure your prediction is accurate. So of course, like there's a way to fix this is that I do loss of recurrent, right? Like I recurse it like 100 times, and then I can make it happen. But of course, this is more consuming, right? Time consuming. But here comes my the one I like, just the backward Euler. Okay, but I do this operator inverse, and here I have a time step 0.5. That's a huge time step, right? If you look at the dynamic, okay. so 0.5. So you see, like from the first image compared with the first image, it's changed already a lot, right? So only based on this kind of image, okay, I use my recursive, PNN, I can recover the bulk potential really well. Of course, you can work on something else, like if because the double value is really trivial, right? It's only like fourth order polynomial. How about if you have a Florin-Hagen, this kind of logarithms, we still can recover it. Okay, not as accurate as it, but still we can recover this potential curves. Can also do Conhealer, right? Like if you have Conhealer equation, you have a bulk potential. You give me a bunch of image, right? Can I recover the bulk potential? Here shows like some comparison. Okay, I fix the time step, but I change how many image I have. Okay, so the first one I only have 2 image, right? A image pair, and that's my prediction. But later if I have five image, okay, this is my comparison. But if I have 10 image, okay, this is my comparison. Apparently, if I have more image, right, even though it's a larger time step, I still can recover the bulk potential. But the one thing I want to emphasize is this approach is quite different with the classical PNN approach, because in their approach, they pretty much have to assume, okay, a single time sequence, right, with very fine like a sampling, and they have to assume like the unknown like potential is the linear combination of certain term. They try to figure out the coefficient. That's what they did in their PNN approach. But in our approach, we don't really have much constraint. Like we can have data pair images from a different sequence, and we can like you can like from one sequence you can have multiple images, right? From another sequence you can another multiple image, and for the image time lag we can have various time steps. So we don't really require much on these like resources. But because like once you tell me the time step, right? Tell me the time lag between the 2 images, I can just do the recursively to time march to that one and do the prediction. Of course, this is only preliminary, right? There are also questions like how to learn like a more complicated like free energy. How about the spatial dynamic? You have the spatial gradient. How about like mobility operators? And so there's how about the other like phase field models? But of course it opens like a more question than what I've solved. But it's interesting field, right? So in this talk, pretty much I introduced some preliminary results on our group on solving and learning phase field models with this neural network. So the first part is that we introduce these adaptive ideas, both spatially and temporally, so that we have like automatic solver to solve phase field models, like in different dimensions and in different like arbitrary domains. The second part is we introduce this pseudo-spectral, we call it recursive PNN, so we can recover the bulk potential from the phase field model. And here are some published references. We do have some ongoing work. It's not available yet. Yeah, sorry, the last slide is important, right? We need to acknowledge the supporters. Yeah. Thanks, guys, for your time. Yeah, that's all I want to say today.
Thank you, Jia. That was, yeah. I mean, the applause was also missing from previous online seminars. That's very nice. Look, this is outstanding work. We like I said, we have been following very closely, and obviously very interested in phase field modeling. So I'd like to open the floor, to anybody who have a question, anybody in the online audience would like to ask a question.
So when is this? This is Jia Zhao.
Hi.
Yeah, hi.
How are you?
Also our collaborator here. So
yeah.
John.
Hey. So I remember you and Levi were working on this adaptive pins. How will this be connected to the work that Jia is doing? Since he's trying to slice the time domain into small chunks and then try to do multiple neural networks. And will your adaptive method be applied somewhere there in the time domain as well? This is a question for witnesses.
Yeah, so hey, Dr. Cal. We don't split the time domain with the self-adaptive pin, not yet. Now that being said, I have implemented and done some baseline preliminary kind of studies in doing like a self-adaptive version of that time adaptive approach where you have maybe 10 neural networks that approximate the domain, and you have some interfaces that you do between them. And the results are pretty good. Some are better than others, depending on some of the parameters you select and how many time partitions you have. And if you do, maybe 3 or 4, you don't get as good results, and maybe 10 to 12. So you can kind of marry the two and do a self-adaptive time adaptive approaches like what we were just looking at. So they kind of coincide in the sense that they are adaptive. They will learn the solution as it progresses. But other than that, it actually more so relates to the loss function weighting that he presented, which was one of his other approaches. That's kind of more what it coincides with. In our case, the weights are learned adaptively instead of being kind of held at a particular value for the training. So they relate, but they are different.
I see.
That's true, yeah. I mean, like the self-adaptive weights, they could be thought of as a resampling of the collocation points, because you put more weights on certain collocation points than others. It's like if a collocation point has very small weight, it's like it's not present. I mean, it doesn't count. Whereas the weight is going to go on the places in the time-space domain where the solution is having trouble converging, right? So it's maybe more related to the sampling approach that even though it's different, but the mechanism is different. But it's a kind of like, it's no longer uniform collocation set. You're weighting the residue points, the collocation.
And with that too, to what we were talking about earlier, the initial condition weights and the early evolution weights, we've noticed play a huge amount into the solution. It's particularly in Alan Kano, we show that plot of weights, and it gets right back into what Jia was talking about earlier, which is that, like he was saying, that you could partition those a little smaller early on in the evolution. A lot of base field is solved with kind of the, you gradually get wider and wider on the time domain as you move through progression. The earlier evolution is way more important. And we've noticed the same thing in the self-adaptive weighting, where the earlier weights, or the earlier collocation weights and the initial condition weights, if you initialize them all to be 1, basically the initial condition weights grow way faster than the collocation weights do. So it kind of learns that on its own, which is a really interesting feature.
Yeah, I think for phase field model, because it's a dissipative dynamic, right? By dissipative, they are not reversible, right? So you have evolving, your energy is dropping with time, which means like all your solution, later solution really depend on your former, previous time step, right? So which means like the previous time step is more important than later. So you do need like lots of weights at the beginning, but you cannot put too much, right? If too much, it still doesn't work. So you have to like wait a little bit more and then gradually like release your weight in the later.
Right. Yeah. Absolutely, that's the case. I mean, I guess diffusion, any diffusion, any PDE involving diffusion, the reaction diffusion.
But the difficulty is like, if it's a diffusion equation, it's okay, because the final steady state is always like more like a constant or something very, very straightforward, right? So for diffusion equation, it's very smooth, so that's the reason you can solve it. But for the phase field, if you change your previous time step solution, later will be changed, right? Yeah. So later we will be like totally different, which means like the previous time step is really important.
Very important.
Yeah.
Yeah.
So, question?
Yeah. Professor Zhao, thank you for your presentation. It's pretty nice. I have 2 questions. The first question is that have you tried your adaptive sampling things to solve some density growth problems, some more realistic microstructure evolution problem? Because like Kobayashi density growth problem because they will involve some different physics and it will be more complicated somehow.
Yeah, but that's a great point. Like, I think so far I'm still not confident enough, right, to apply it. Like, that's the reason all my problem is toy problem, because I know more like in the physics field there are lots of more equations. Like my matter like works on Alan Concater, but because right now we're working with some collaborators on this like a copolymer dynamics. The interface is more sharp, and then it won't work anymore. And then you see, I still try to make sure it can solve the general physics field when I know, right? Then I can try to apply it to more general cases.
Yeah, because in my PhD dissertation, we are trying to use the things to solve to predict the microstructure evolution, the density growth. We try by embedding different physics like the heat transfer, transition, and solutions all together.
Yeah.
When we try to predict the density growth, the results are not very good. The primary arm shape it agrees well, but for the secondary arm spacing or like those defined details, we cannot approximate very well. So that could be an issue, and we haven't found we are still trying to improve the means to how can we solve some real materials problem rather than just like the simple brain growth.
Yeah, because for physics field model, if even you solve them numerically, it's not trivial. Like then you want to use the neural network, because neural network is more like you have to use a single precision. It's more like coarse, right? Not that accurate. And then it's really tough.
The second question is I really like your idea about the pseudo spatial recursive things to discover the free energy form. Especially it's not like just you try to discover the question, you try to discover the free energy form. And my question is that what is the computational efficiency when you use this implicit form to solve to discover how fast is it compared to the explicit way to solve?
Yeah. Thanks for the question. Well, first of all, I don't think the implicit approach can solve this problem. The problem I'm talking about, right? Like right now, I think the highlight in this pseudo spectral matter is, so if your sampling is very coarse, right? It's not a very fine sampling. Like you have one sample, but after a long time you have another sample, and the other is like you do have some sample, but this sample not from the same experiment. In other words, they are not from the same time sequence. Like in this experiment, you do have a few images, right? Only like 3 or 4 images. But in next experiment, you have 3 or 4 images. So they are not from the same sequence. So I don't think the classical PN or this hidden physics model really they propose can work out. Because they have to first of all feed the solution with a neural network, right? They have and then they plug this into the equation, and then they have first of all they have a neural network to feed the solution, and then they have to assume, okay, your sequence is very refined, and your sequence is the same time sequence, and then you can do next. But right now my constraint is way much weaker than theirs. So that's the first part. The second part is because I use a pseudo spectral. So in the whole thing is you're using FFT and then do the inverse. So time is relatively cheap, right? So even though I have an inverse operator, but it's very easy to calculate. So in the end, it's not that hard, to use this approach to solve the inverse problem. Yeah.
Would you know how to apply inverse modeling with the time sampling, like the progressive time marching? Would you know how to assimilate data?
Yeah, that's a different story. Yeah, I recently started to think about those like data simulation, order reduction, but that's not my field. I'm still learning it.
That's interesting.
Yeah, that's a good suggestion. Yeah, that'd be great.
Is there any question from the online audience? No. So go ahead, George.
Yeah, I was just going to ask. So a couple of slides ago, you showed like a two-dimensional, looked like maybe a spinodal decomposition problem with the Cahn-Hilliard, and I think it was in reference to exactly.
Sorry, what?
So a couple of slides, you just passed it, where you had the evolution of Alencon. That was it. There you go.
Oh, this one. Okay.
Perfect. Right. So so those results you showed on the bottom, these were high fidelity solution results, right?
Yes.
Okay. So these are, yeah. So my question was, have you applied any or have you tried to use any of your time marching methods or the sampling methods to solve a two-dimensional Cahn-Hilliard problem such as this one, where you have an initial randomizations, a homogeneous material maybe there, and you tried to show a decomposition with the homogeneous material initialization, such as this one. Does that question make sense?
Can you explain again? Sorry, I didn't quite get your question.
Yeah, so you showed the kissing dots, right, with Cahn-Hilliard in two-dimension. So have you tried a problem like this one, where you initialize a homogeneous material and then try to show its decomposition using pins?
Yeah, I see. Yeah, but no, I think that this is all toy problem, right? Try to solve simplify the problem first. But you see, for the Cahn-Hilliard equation, I still cannot make it perfect. Then I'm reluctant, to move on, because in the end I have to come back again, to fix it, right? So, yeah.
Okay, yeah, I was curious. I mean, I've been trying myself. I just wondered if you had any luck.
But yeah, but I think also they're great. I think you guys are definitely more, I would say, more advanced than me in terms of applications, in this field. Yeah.
Good stuff. This is good stuff. In general, yeah, I like the capabilities of neural networks in inverse problems, right? So, inverse problems where you cannot solve these problems with traditional numerical methods. And this example you have here is a very good, it's a very nice example of an inverse problem that you solve with the neural network. So that's very nice.
Yeah, thanks.
Any other questions? Okay, so it's 3 o'clock. So I'm sorry, 4 o'clock. 4. And
thanks everyone for being here.
Yes, I'm gonna now, and thank you again, Jia. And like I said, the invitation is there for when the pandemic subsides, whenever that is, for you to come here and visit us. And we really appreciate your taking the time to give us a seminar here today.
Yeah, thanks for having me. Actually, I said, I check out you guys' work. It's really nice. So I'm asking my students because you guys post your code, so you're more generous. They're trying to, to put a little bit more constraints, right? So using this, you have this more like a Lagrange multiplier, so you can, changing the weight automatically, later. I think that's a great idea. I believe, it can be further exploited, to solve the phase field models.
Please let us know how it goes.
Yeah.
Yes. Thank you.
Absolutely. Yeah. Thanks for the job.
Thank you very much.
Yeah. Thanks, guys. Yeah, bye.
So we will